Welcome back. A few lectures ago we talked about how we can actually use some filtering operations to move between scales in our wavelet scaling spaces. And the idea is that if we have the signal at a very fine space, let's say Sj+1, if we want to go to the coarser space, we can utilize two filters, H0 and H1. And for the Haar wavelets, these two filters are derived from the relationship between the wavelets at different scales. So we found boxed here in red that phi, the scaling function at j comma n, is just equal to a scaled version of two scaling functions at a lower scale. And so that gave us 1 over the square root of 2 delta n plus 1 over the square root of 2 delta n minus 1 as our filter coefficients. When we're done, we use two scaling functions to get at scale j+1, so we only need one scaling function at scale j. And so we downsample by 2. And the same thing goes on for the wavelets. Well, we're going to spend a little more time today talking about that. So, as some context here, we have x at scale j, is equal to the projection on scale onto the scaling space j-1 of x, plus projection onto the wavelet space j-1 of x. And we've already worked out an expression for that, as shown here. That's equal to, our projections are equal to the sum over all shifts of our scaling coefficient times the corresponding scaling function, plus for the wavelets it's the same thing, sum of all possible shifts, the wavelet coefficient times the wavelet itself, the wavelet function, the basis. And there we go. And we showed then that these, because of the relationships between the scaling functions and by the linearity of the projection operation, it becomes clear that Sj of n is equal to these Sj-1 of n plus the wavelet function, as we described previously. Okay, so we can iterate on this. Let me see if I can select and move this. So, if we can do that to get Sj from Sj-1, we can obviously do the same operation to get Sj-1 from Sj-2 and Wj-2. So what do we have here? Now we're building up our function from the Sj-2's and the wavelets. So, and once again, our target is this Sj. As you may recall, Sj is actually the highest resolution, or the finest scale. And as we go down, Sj-1 is a coarser scale. So once again, we're going from fine scales to coarser scales. Now, the way we've expressed this, it looks like we're building up Sj, at least the way I've explained it, We're building up Sj from Sj minus 2 and Wj minus 2 and Wj minus 1, but we're not. We're showing the relationship between them. And if you look at the arrows here, you see that they're all going to the right. So it's assuming then that we have we already have our signal at the finest scale. And as we said before, this might be considered, for example, to be samples, digital samples of our signal. And ideally, we've obtained those samples using a projection onto a wavelet. In practice, maybe that's not the case, but we'll let it slide for right now. So what we have now is we start with the fine scale, and we show that that's equivalent to these coarser scales. Now Wj minus 1 isn't that coarse, but Wj minus 2 is a little bit coarser. And we can continue doing this. In wavelet analysis, we always do this on, we always break down the scaling function projection and not the wavelet. So once we've pulled off wavelet coefficients, we just keep those. But the scaling coefficients, which would be right here in blue, we continue to break down till we get all the way down to the coarsest scale that we are interested in, S0 in this case. Well, the big question is, how do we we've started at the finest scale, which you may argue is what we're most interested in. We'd really like a fine scale version of the signal. Maybe we don't want all these rough scales. Well, if we've chosen our wavelets well, we've started by just discussing the Haar wavelets, and I've introduced you to the Dawashis also, but we haven't gone very much in depth with those. But if we've chosen them well, then maybe these coarser scales of the wavelet function and the scaling function or coefficients are useful. And in fact, since the H0 filter tends to be a low-pass filter and H1 tends to be a high-pass filter, this is a way of doing frequency analysis on a signal, or breaking down maybe a signal into a space where it's more easily compressed, where we have a low frequency version and then we just add in the details, and we may decide to discard some of those details, as we did with JPEG compression. Alright, so I'm going to throw this on the next slide here and get going. Okay, so Filterbanks Part 2. This is where we start getting to something useful and some analysis perhaps that we can really use. So I'm going to kind of run through a little bit of discussion here first about the Z-transform, because the Z-transform, you've most likely seen it before in other signal processing classes, but most classes, undergraduate level, don't spend a lot of time discussing what happens when we have things such as upsampling and downsampling. So just as a quick aside, the Z-transform of a signal, x in this case, is equal to x of n summed over all n times the to the minus n. NZ is a complex number. And as you recall, it's related to the to the discrete time Fourier transform. In fact, it's a generalization of the discrete time Fourier transform when z is equal to e to the j omega instead of okay. So we also know, for example, that if we have a filtering x of n convolved with h of n, that implies that x of z would be multiplied by h of z in the z transform domain. Okay, so let's see what happens when we do downsampling. So suppose that y of n is equal to x 2 of n. So what's the relationship between x of z and y of z? Let's try this out. Y of z would be the sum over all n of x 2n, and since we're only sampling, for each integer value of n, we're sampling every other value of x. This is our downsampling operation. So this is identical to this sum. L all even L x of L z minus L over 2. Well, how do we get even numbers? We know how to get even numbers. One way to do it is to say something like 1/2 x n plus 1/2 of minus 1 to the n x n. So what would this do? Well, when n is 0, we have 1/2 x of 0 plus 1/2 x of 0, and we're good. When n is 1, we have 1/2 of x of 1 minus 1/2 of x of 1, and that disappears. X of 2, once again, we are summing 1/2 x of 2 plus 1/2 x of 2, and so we get x of 2. So this is a nice way of getting just the even values of x. So we can apply that here, and we get 1/2, and now we can just sum over all the L's. We don't have to worry about even or odd, because we're going to take care of that with our new handy formula, z minus L over 2 plus 1/2 sum L equals minus infinity to infinity xl minus 1 L z minus L over 2. Now you already know that when we get rid of samples, we run the risk of aliasing. How's that going to show up? It turns out that the whole sampling aliasing thing falls out of the math that we're doing right now. this a little differently. Now, this looks just like the z-transform. Well, almost just like the z-transform, except we've got this z to the 1/2 instead. So we can write this then simply as 1/2 x z to the 1/2 plus x minus z to the 1/2. And we're done. So that's y of z. When x of n, and now y of n, is equal to x to n. So where does the aliasing come in? Just as an aside, note that the DTFT is related to this, as we said. So by just substituting e to the j omega for z, that says that y e to the j omega is equal to 1/2 x e j omega over 2 plus x e minus j omega over 2. So this part, the omega over 2, now tells us that what used to be at 2 pi is now a pi. So our replicated frequencies are squishing in towards the origin, as what happens when we have aliasing. And this part is an additional part that's added in and overlaps with what we already had. So we have aliasing. So let's see, how do we show that? Well, if, for example, we said omega is equal to, let's call it omega tilde is equal to omega plus 2 pi, that's okay, because e to the anything plus 2 pi, j2 pi, is equal to what it was before. But when we have the over 2 factor in there, we end up getting our omega over 2 plus pi. So we have now a time-dilated version shifted by pi and added on back to our original term. So that's a potential aliasing term showing up right there. Okay, and I think I express this differently. When we divide by 2 here, it's not squishing in from 2 pi out. This is taking something that might look like that and turning it into something wider. So if this was pi, pi is now there. And then this term is taking what was here and spreading it to there. And so here we have our aliasing term. Okay, now we also talked about upsampling. What happens when we do upsampling, it's a little bit easier, but I guess we're going to have to go on to the next slide. So let's do this. So we want to know what y of z is. When we stick zeros in between every sample of x, that's our upsampling. So we start with an x that looks like so, and y looks like and so on. Okay, so we can do similar analysis to what we did just a moment ago. We have y of z is equal to the sum minus infinity to infinity, y of n, z to the minus n, and let's expand that out. When n is even, we have x n over 2, z to the negative n, which of course is pretty easy with a change of variable. Now we can get L going from all negative infinity to infinity, and let L equal 2n, or n equal 2L rather. Negative in there. So that's just equal to the sum for all L, x L z squared to the minus L, and so that would be x of z squared. So this does the compression of the DTFT waveform. Okay, so now that we've established this basic result, let's go back and take a look at what happens when we put all of this together. First, let's make a new slide and make this one topic per slide. Filterbanks. So, the idea here is that we would really like to find some way to invert this particular transform. And it probably shouldn't strain credulity, to find that we can do this. But how? So back to our motivational starting point. Right here, we're going to invert the structure with another filter bank. So let's let G naught of n. Let's focus on the Haar. Haar perfect reconstruction. And we'll let G naught of n equal H naught minus n. And so that's going to be 1 over the square root of 2 for n equals 0 and 1 and 0 otherwise. So really, in the case of the Haar wavelet, G naught is just equal to H of n because of the way it's constructed. It has the same shape, in other words. And we'll have 1 over the square root of 2 for n equals 0, 1 over the square root of 2 for n equals 1, negative, and 0 otherwise. Okay, so is this going to do the trick? Well, recall that we have Sj minus 1 of n is equal to 1 over the square root of 2 x2n plus x2n plus 1. So, looking back up here, this value right here, u of n, put it right there. Un will be 1/2 x of n plus x n plus 1 for n even, and 1/2 x n minus 1 plus x of n for n odd. So the values kind of show up in these pairs. We've added them together and mixed them up, and it's kind of hard to undo that. But fortunately, yeah, so what would this look like? We would have something like u of 0 is going to be x of 0 plus x of 1, and u of 1 is going to be going to use x of 0 and x of 1 again. So, and this continues. Every other sample is repeated. So we'd see the same. X of 2 and x of 3 would be the same, and so on and so forth. Okay, so following similar math, we get V of n. V of n is the lower branch here, based on the wavelet scaling coefficients instead of, or wavelet coefficients instead of the scaling coefficients. So this is just going to be 1/2 x of n minus xn plus 1 for n even, and 1/2 of the difference here, but with a sign change, minus xn minus 1 plus xn for n odd. And so these also appear in pairs, but like this. V naught is going to be equal to negative V1 equal to 1/2 x naught minus x1, and same thing, V2 is equal to negative V3, and so on. So now when we add these together, x tilde of n is going to be u of n plus v of n. And we can see that right up here. So let's see, when we look back at these equations, when n is even, the x of n plus 1's cancel out, and we get 1/2 x of n plus 1/2 x of n will be x of n. When x is odd, the x of n minus 1's cancel out, leaving us with the x of n's again. So this is just equal to x of n for all n. And since we have this as a repeating structure, let's go back and take a look at that. If we can reconstruct that point from S naught and W naught using our inverse filters, then we could work our way back down the chain to the left and reconstruct the whole tree. So we'll have an inverse tree that can reconstruct our signals to arbitrary levels.